చెప్పేటప్పుడేగా బోర్డు
ఓన్లీ క్లాస్ రాసుకోవడానికి టైం ఇచ్చినప్పుడు మాత్రం అటే వెళ్ళండి 2 మార్క్స్ క్లాస్.
Okay, continues to the previous session question. Now this is C of s by R of s equal to this one, and we already find the order. There are two closed loop poles, therefore order equal to 2. And then here which we already covered, there are two time constants coming, but what I am saying is we have two time constants, but the control system will have only one time constant. So for getting one time constant, then what should be, we have to be identified. We want to eliminate one pole and we want to consider only another pole. But here these two are two closed loop poles, both are important. We will see how to find only one single time constant. And one more thing is here, frequency of oscillations. This is the frequency of oscillations. Now for finding the frequency of oscillations, then we have one shortcut method. Then who will give the frequency of oscillation directly? The frequency of oscillation will give directly the imaginary part. The imaginary part will give directly the frequency of oscillation. Now imaginary part of pole. Now see here, what is the imaginary part of pole? Now this is a closed loop 0, forget about that. Then this is a closed loop pole real part. This is also closed loop pole real part. Is there an imaginary part? No imaginary part, because the pole will not having any imaginary part. Therefore it is having only real part, no imaginary part. Poles are having only real part. There is no imaginary part. Poles are having only real part. There is no imaginary part. Poles are having only real part. There is no imaginary part. Therefore, if the imaginary part is 0, therefore you tell me what is the frequency of oscillation present? There is no imaginary part. Therefore, the frequency of oscillation present is 0 radians per second. There is no imaginary part, which means that the imaginary part is 0. Therefore, omega equals 0. Frequency of oscillation is 0 radians per second. Therefore, now there are two questions which we all finished. One is order, which are completed, and another one is frequency of oscillation, which is completed. But for finding time constant, we have some confusion with the two time constants, but we have only one time constant, that we will see. Okay, now take this one. So poles are having only real part, no imaginary part. Therefore, frequency of oscillation is 0 radians per second. Therefore, order is completed, frequency of oscillation is completed, time constant we have some confusion that we will see. Then he is saying draw the response in time domain. So if you want to draw the response, from the response we can decide the system stability. Now in that concept we will finish this time constant also. Now see here, Now this is the response output, which is equal to input into s plus 1 by s plus 2 into s plus 3, which means that if you want the response, if you want to find the response, first we want to apply the input. Am I not? We want to give the input, then only we can say that you can get the response. That's what we start with, different types of inputs. Now it is available. What are the different types of inputs available? Now which input we have to be considered? Right? Now we are in the theoretical analysis. We have the theoretical calculations. Now I am already saying that for theoretical calculations, for mathematical calculations, what is the best input? For theoretical responses, for theoretical calculations, the best input is an impulse input. Therefore, now for theoretical calculations, for the theoretical responses, then the best input is impulse input. Therefore, for theoretical calculations, now I am taking this is the reference input, which is nothing but impulse input, R of t, which is equal to delta of t, which is impulse input. Now this is R of t, which is equal to delta of t, which is impulse input. Therefore, what is R of s? R of s, which is equal to Laplace transformation of R of t, Laplace transformation of R of t, which is Laplace transformation of delta of t, which is equal to 1. Therefore, this is a reference input, this is impulse input, R of s equal to Laplace transformation of delta of t, which is equal to 1. Therefore, now see here, C of s, which is equal to R of s equal to 1 into s plus 1 by s plus 2 into s plus 3. Now if R of s equal to 1, which means that you are applying which input? Impulse input. If you are applying impulse input, then that response, what I am saying, this is impulse input. Therefore, this response is nothing but, this is the impulse response. This is the closed loop control system response is nothing but impulse response. This is impulse response. This is the closed loop control system response, which is nothing but impulse response. Now see here, now I am applying impulse input, therefore this response is nothing but the impulse response. Because the question is mentioned, draw the response in time domain. So this is the impulse response. Now, but this is in which domain? Frequency domain. But I want in time domain. Therefore, C of s, which is equal to, now this is the response in frequency domain, but I want in time domain. Therefore, I go for partial fraction a by s plus 2 plus b by s plus 3. A by s plus 2 plus b by s plus 3. Now see here, C of s equal to a by s plus 2 plus b by s plus 3. Therefore, now find the constants of a and b. Now s plus 2 cancel. Now a by s plus 2 cancel, and remaining portion is s plus 1 by s plus 3. For finding a, substitute s equal to minus 2. Similarly, s plus 3 cancel. For finding b, substitute s equal to minus 3 and s plus 1 by s plus 2. For finding a, s plus 2 cancel and substitute s equal to minus 2 here, and for finding b, s plus 3 cancel and substitute s equal to minus 3. Therefore, what is the a value? Minus 2 plus 1, minus 2 plus 3, which is nothing but minus 1. Now s equal to minus 3, minus 3 plus 1, minus 3 plus 2, therefore minus 2 by minus 1, which is equal to 2. Now here A equal to -1, B equal to 2. Substitute here. A equal to -1 by S plus 2 plus B equal to 2 by S plus 3. This is C of S. Now this is a closed loop control system response, but this is in which domain? Frequency domain. I want closed loop control system response in time domain. Therefore what we are doing? Apply inverse Laplace transformation. Apply inverse Laplace transformation. Now see here, if I apply the inverse Laplace transformation, that's what in the first classes I am giving all the formulas. Those formulas are frequently repeated. That's what I am giving those formulas. Therefore, if you apply the inverse Laplace transformation, the inverse Laplace transformation of C of S is C of t, which is equal to -1 into, what is inverse Laplace transformation of? What is inverse Laplace transformation of 1 by S plus 2? E power -2t plus 2 into, what is inverse Laplace transformation of 1 by S plus 3? E power -2t. Now 1 by S plus 2 inverse Laplace transformation is e power -2t. 1 by S plus 3 inverse Laplace transformation is e power -3t. Now this is closed loop control system response. This is closed loop control system response, or this is the closed loop control system response, or impulse response. Impulse response. In which domain? This is the closed loop control system response or impulse response in time domain. Now see here, this is the closed loop control system response. This is the impulse response in time domain. Because what he is asking is, draw the response in time domain. Now before we draw the response, now first we will see the response in time domain. This is the response in time domain. Now you can easily draw the response. Now first you take this copy. Okay. Now see here. Now this is the closed loop control system response. This is the closed loop control system response, and this is the impulse response. This is the closed loop control system response or impulse response in time domain. Then if you observe here, now your closed loop control system consisting of closed loop 0 and 2 closed loop poles. This is closed loop pole and this is closed loop pole. Now your closed loop control system consisting of 1 closed loop 0 and 2 closed loop poles. 1 closed loop 0, 2 closed loop poles. But what happened here? Then this is closed loop control system. System consisting of 1 0 and 2 closed loop poles. Whereas system response consisting of what? The response consisting of only -2, only -3. The system consisting of both zeros and poles, the system consisting of both zeros and poles, but the system response consisting only -2, -3. -2, -3 is nothing but poles. Therefore, what we have to conclude it here? Therefore, the system response, the system behavior is decided by -2, -3. -2, -3 is nothing but only closed loop poles, but there is no -1. The -1, the 0 is there in the system, but it is not there in the system response. Then this is very important point, which means that then this particular point also you know down. Closed loop control system consisting both poles and zeros, but closed loop control system response means output response consisting only poles but not then you understand? Now this is the example for that. Now the closed loop control system consisting both zeros and poles, but closed loop control system response consisting only -2 and -3, which is nothing but only closed loop poles. This is a very important and easy statement for you, which means that the response, the output is decided only on poles. Therefore, the response, the behavior is decided by only poles but not zeros. Its response is decided, the response is consisting only poles. Therefore, the output, the behavior is depends only on the poles but not the zeros. That is the reason why for finding the system time constant we consider only poles, we are not considering the zeros. Okay, that is very clear statement here. Okay, take down this note also, which is very important. See, this is not in this particular question I am talking about. This statement is not only for this particular question. You take any closed loop control system and give some input and see the response. That response consisting only poles but not zeros. That's why the system complete behavior is depends upon only poles. That's why in the first session we will see the characteristics, the closed loop control system characteristics is decided by only closed loop poles. That's why the system time constant is one of the characteristics which we can find only from the poles location but not from the zeros location. Right. Now this is the response. So this is the response in time domain. Then we want to draw the response. Yes, we will try to draw the response. Now, before we draw the response, then one important point we have to be identified. And this is one closed loop 0. Therefore, the system from this problem you want to be understand, you want to be identified. Therefore, the system complete behavior is depends only on the poles location but not the zeros location. This is closed loop 0. This is closed loop pole -2 and -3. This is closed loop 0, not at all useful. This is closed loop pole. The behavior is completely depends upon closed loop pole only. Now, see here. Now I want to draw the response. Now this is closed loop pole. This is closed loop pole. The response, the closed loop control system response is completely depends upon closed loop poles. Therefore, now see here, this is the pole which is nearer to the origin or nearer to the imaginary axis. This is the pole which is nearer to the origin or imaginary axis. This particular pole is called as dominant pole. The pole which is nearer to the origin or imaginary axis, that particular pole is called as dominant pole. And similarly, the pole which is away from the origin or away from the imaginary axis, that particular pole is called as insignificant pole. The pole which is nearer to the origin or imaginary axis, that pole is called as dominant pole, and the pole which is away from the imaginary axis or origin is called as insignificant pole. But both are closed loop poles. Now the question is, what is the dominant pole transfer function? Now see here, you know that the dominant pole transfer function is 1 by s plus 2. The dominant pole transfer function is 1 by s plus 2. What is its inverse? The dominant pole transfer function is, pole means denominator, 1 by s plus 2. What is its inverse Laplace transformation? Some constant into e power minus 2t. What is the dominant pole response? Now this is the dominant pole response, which is nothing but the response is exponentially decaying. Now t equal to 0, some k1 into exponentially decaying. This is the dominant pole response. Is it right or not? This is dominant pole response. This is the dominant pole response, which is exponentially decaying. Next one is, now see here, this is the insignificant pole, right? But what he is doing is, this is the dominant pole. The dominant pole is 1 by s plus 2. Now this is the dominant pole, and the dominant pole transformation is k1 into e power minus 2, which is exponentially decaying. Now see here, now what we are doing is, once if you see the dominant pole, now here we will find directly the overall closed loop control system response. What is the overall closed loop control system response? Overall closed loop control system response. The overall closed loop control system response, generally we are decided with the controlled output, controlled response C of t. Then he is saying the overall closed loop control system response, the overall closed loop control system response, which you are saying is exponentially decaying. The overall closed loop control system response is exponentially the overall closed loop control system response, which is exponentially decaying. Now, how you decided that? How you can decided that? Now see here. Now this is the dominant pole response. Now you are writing the dominant pole response is exponential decaying. By looking this dominant pole, then you decided the overall closed loop control system response. The overall closed loop control system response, you are saying exponential decaying by looking the dominant pole or not? Is the correct way to decided the overall closed loop control system response, which is exponentially decaying, by looking the dominant pole? Tell me, is it the correct way? You are not considering 0 is acceptable because the zeros are not there in the response. It is there only in the system. But this is closed loop pole, and this one is also the closed loop pole. This one is a closed loop pole. Same importance is there. Same importance is of that this particular closed loop pole or not? Now minus 2 is important because this is the closed loop pole. Minus 3 is also important because this is also a closed loop pole. But you are not consider this closed loop pole, and you consider only this closed loop pole, and you decided the closed loop control system response is not at all a correct way. Am I right or not? But what you are doing is, you are not take care of insignificant pole, you care of only dominant pole, and you decided the overall closed loop control system response is the correct method or not. You want to identify a minute. That what I am saying is, no sir, this is closed loop pole sir, this is also closed loop pole sir, then how you can decided the overall closed loop control system response only by looking the dominant pole? No. Therefore, now is there any problem if you are not considering the insignificant pole? There is no effect if there is not considering the insignificant pole, then the response is not having any problem. Then you just ask the insignificant pole. What the insignificant pole saying is, the insignificant pole is saying what? The insignificant pole transformation is 1 by s plus 3 and its inverse Laplace transformation is k2 into e power minus 3t, and the response is exponentially decaying. Now this is the insignificant pole response. Insignificant pole response. This is the insignificant pole response. Then what the insignificant pole is doing? The insignificant pole response is just simply follows the dominant pole. That is the reason why if you consider the insignificant pole, or if you are not consider the insignificant pole, the dominant pole response will not be disturbed. Even if you consider the insignificant pole, even if you are not consider the insignificant pole, the dominant pole response does not disturb. Even if you add the insignificant pole, or if you are not add the insignificant pole to the dominant pole response does not disturb. Therefore, you can decide it the overall closed loop control system response by looking at dominant pole is the correct method. Even if you consider this one, even if you are not consider the insignificant pole, then not a problem. The overall closed loop control system response will not be disturbed. The overall closed loop control system response is exponentially decaying by looking the dominant pole, and the dominant pole response does not disturbed by its insignificant pole. Therefore, not at all a problem. The overall closed loop control system response you decided from the dominant pole. Understand or not? Therefore, so you understand now. Previously, for finding time constant, there is a problem, and you take one note also that here in this problem we have two time constant, but control system will have only one time constant. If you want to take only one time constant, we need only one pole. Then you tell me which pole we have to be considered. You have to be consider an insignificant pole, or you have to be consider a dominant pole. You decided. Then obviously it should be a dominant pole, because the overall closed loop control system response is decided from the dominant pole. If you are not considered the insignificant pole, or if you are considered the insignificant pole, not a problem, not a issue. The dominant pole response does not disturb. Therefore, overall control system response is also not disturbed. Therefore, for finding the system time constant, we have to consider the dominant pole only. Then now you find the system time constant formula. Okay, then what is the system time constant formula? Now you tell me the system time constant formula, which is nothing but negative of reciprocal of real part. Previously you are saying real part of pole. Now this is negative of reciprocal of real part of which pole? Dominant pole. Real part of dominant pole. Now this is negative of reciprocal of. Now this is a system time constant. The system time constant, which is nothing but negative of reciprocal of real part of dominant pole. Then now you tell me the system time constant, which is nothing but negative of reciprocal of real part of dominant pole. What is the real part of dominant pole? The real part of dominant pole, which is equal to -2. Therefore, minus cancel. Therefore, which is equal to 1 by 2, which is equal to 0.2 5 seconds. This is the system time constant. Now this is the system time constant, the parameter which is coming, and this is the system time constant standard formula. Now whether it is a 1 pole or a 2 poles or a 3 poles or any number of poles, then which pole you have to consider? You have to consider the dominant pole. We have to be considered the dominant pole, and for any particular problem you consider the dominant pole, and the system will have only a single time constant. Now there is no 2 time constant, and this particular problem will have only 1 time constant. Therefore order is completed, time constant is completed, frequency of oscillation is also completed, and draw the response in time domain. Now in this particular response we have a concept of dominant pole and insignificant pole. Okay, now you take this one, and from the response then we will find the system stability. How to find the system stability we will see. Okay, now this is the way how to find the system time constant, negative of reciprocal of real part of dominant pole, and this is the dominant pole and this is the insignificant pole, and this is the closed loop control system response. Now see here, now this is the response. Then what is the response? Now in the question he is asking draw the response in time domain. Now this is the response, draw the response in time domain. Now the response is exponentially decaying. This is with respect to time. Now draw the response in time domain. The response is exponentially decaying with respect to time. Now the next, once if you have the response, now see here, input we are applying and we just see the response. From the response now I want to decide the system stability. Yes, see this response and decided the system stability. From the response then how to decide the system stability. Then the response is available to you. Now see the response. Now this is the response, right? Now see here, response, output, see the output. From the output you decided the system stability and the cycle is also completed. Input I am giving, response. Now this is the response which are available to you. From the response we want to decide the system stability. So this is the response. Now see here, with respect to time, then on the time axis you apply the inputs. On the time axis you apply the inputs. When you are applying the inputs, now the response is follows the input or not. Now this is the input 1 input at t1 seconds, at t2 seconds, at t3 seconds, at t1 seconds, at t2 seconds, at t3 seconds, at t4 seconds. If you are applying the input on the time axis, this response, this output is follows the input or not follows the input. If the response is follows the input, if the response is follows the input, then that system is said to be stable. This is a stable system. How you decided the system stability? From the response, because the response is follows the input, then the system is stable. Yes, this is a stable system. Now, then I am giving one shortcut method to you. The response is follows the input, therefore the system is stable. Therefore, no sir, now by looking this response, I am not in a position to identify, then this response is exponential decaying, then how I can say the system stability? Then very simple question. The response, if you apply the inputs on the time axis, this fellow is follows the input with respect to time, then the system is stable. The response follows the input, then assume their inputs is on the time axis, then the response is follows the input, system is stable. I am applying the inputs on the time axis, the response is follows the input, then that particular response is a stable response and that particular system is a stable system. No sir, this is somewhat difficult for me to draw the response and everything. Is there any easy method? Is there any easy shortcut method to decide the system stability? Yes, there is a shortcut method. Now for that shortcut method, now you just see here, what is our purpose? Our purpose is to decide the closed loop control system stability. Closed loop control system stability. I want to find closed loop control system stability. I want to find the closed loop control system stability. To find the closed loop control system stability, now for finding the system stability, that stability we can decide it only from response. Therefore, for finding the system stability, we want to see the closed loop control system response. See here, see the cycle. Stability, if you want to find, see the response. From the response, you decided the system stability. Therefore, to decide the system stability, then see the response. Yes, this is the response. Then just now we have to identify the response consisting what? What is the response you are getting for this particular problem? What is the response you are getting? See here, this is the response or not? C of t you are getting as minus 1 into e power minus 2t plus 2 into e power minus 3t. Then you already identify that this minus 2 and this minus 3, this minus 2 and this minus 3 is nothing but closed loop pole, closed loop pole. So the closed loop control system stability is obtained from closed loop control system response, and the closed loop control system response consisting only closed loop poles. Now the closed loop control system stability is identify the closed loop control system response, the response consisting only closed loop poles. The finally what we conclude here, for finding stability you have to see the response. For the response, in the response consisting only poles, it doesn't consisting any zeros. Now therefore, from this we have one shortcut method directly. You can decide the system stability from the closed loop poles. This is a cycle now just repeated everywhere. Stability we want to find, that stability we are finding by looking its response, the response consisting only closed loop poles. Therefore, from the closed loop poles, you can decide the closed loop control system stability. This is a direct shortcut method. Instead of doing this lengthy procedure, you have to go back, you have to go to this shortcut method directly. Therefore, what is the shortcut method? You want to find the stability, then see the closed loop poles. Now, where is the closed loop poles? This is the closed loop pole. Now, see here, this is the closed loop poles in the S plane. Now, from this closed loop poles, you decided the system stability. Now, where are the closed loop poles? Now, this is your closed loop pole. You just see here. This is your closed loop pole. Now, these are the closed loop poles. Now, where is our closed loop poles? And if you observed or not, in the first session, we will see the S-plane is divided into three parts. One is left-hand side of S-plane, right-hand side of S-plane, and imaginary part of the S-plane. Now, where is your closed loop poles? Now, your closed loop poles lies on left-hand side of S-plane. Now, your closed loop poles lies on, if your closed loop poles lies on left-hand side of S-plane, if your closed loop poles lies on left-hand side of S-plane, therefore closed loop control system is directly stable. Very simple. If your closed loop poles, and then there is no need to apply the input, response, and all these things are not required. Then if the closed loop control system stability, if you want to find, just see the poles location. If your closed loop poles lies on the left hand side of S-plane, 100% the closed loop control system is stable, because the response should be a stable response. The response is follows the input. Now I think all the questions, all the parameters what he is asking in the question number 4 is finished or not. What is question number 4 he is asking? You just recollect the question number 4 in your handbook, right? Now in this question, I just revised. In this question he is asking order. Therefore there are two closed loop poles, order equal to 2. First question is completed. Next question. Now frequency of oscillation. Now is there any imaginary part? No imaginary part. Therefore frequency of oscillation is 0 radians per second. You decided already by looking the poles, real part and imaginary part. Now the question, that is cross check. Then frequency of oscillation, how much you are getting? There is no imaginary part, only real part. Therefore the frequency of oscillation, there is only real part. Therefore the frequency of oscillation, no imaginary part, only real part. Therefore frequency of oscillation 0 radians per second, which we already finished. No imaginary part, only real part. Therefore frequency of oscillation is 0 radians per second. But what is the frequency of oscillation in the response is 0 radians per second. But what the response is saying? See the response. This is the overall closed loop control system response. This is the overall closed loop control system response. Now in this overall closed loop control system response, this response is having any oscillations? Is there any sine wave? Is there any cos wave? No. This response does not having any oscillations. Therefore the frequency of oscillation is, then you just compare. This is the overall closed loop control system response. The overall closed loop control system response is, this is the overall closed loop control system response. Now this response is exponentially, decaying. Now see here, this is the overall closed loop control system response, which is exponential decaying. Is there any oscillations? No, no oscillations. Is there any sinusoidal nature here? No sinusoidal nature. Therefore the frequency of oscillation is 0 radians per second. The frequency of oscillation is 0 radians per second. Now this is the frequency of oscillations in the response. Now this response does not having any frequency of oscillation, and the imaginary part is also not there. Therefore this is the frequency of oscillation from the pole imaginary part, and this is the frequency of oscillation in the response. Both are matching or not, and the response is follows the input. The response, if you are applying the inputs here, the response is follows the input. Therefore this system is a stable system. Stable response. Now this is the stable response, and that particular system is nothing but stable system. Now all the questions which we are finished, now he is asking order is completed, he is asking time constant is also completed. The time constant is nothing but negative of reciprocal of real part of dominant pole. Okay, that formula is also important. And frequency of oscillation is completed, and draw the response in time domain is also completed, and from the response you decided the system stability. Now that is also completed. Okay, now this is question number 4, all the parameters which we are completed, and we will find one important formula from that. Time constant is nothing but negative of reciprocal of real part of dominant pole. Real part of dominant pole. This is the standard formula for any number of poles. This is the time constant, the negative of reciprocal of real part of dominant pole for anything. 1 pole or 2 pole or 3 poles or anything. Okay, and 2 closed loop poles and order equal to 2. Then all the parameters which we are completed here, and just I am giving this one. 2 closed loop poles. Therefore order which is equal to 2. Then once again you take everything. Okay, then in that particular question number 4 is having all the parameters what we is asking. Order is 2 closed loop poles, and response is exponential decaying, system is stable, and time constant which is also completed, and this is frequency of oscillation. Everything will be completed. Take this one. Okay, now see the definition of dominant pole here. What is the dominant pole? Dominant pole is a pole which is nearer to the origin or imaginary axis, or you can say like this also. What is the time constant? -1 by -2. Time constant equal to 0.5 seconds. And this is dominant pole. What is insignificant pole? The pole which is away from the origin or imaginary axis. Therefore, this is away from the origin or imaginary axis. And what is the time constant? -1 by -3. Therefore, time constant equal to 0.33 seconds. Therefore, now what is the definition of time constant? What is the definition of dominant pole? There are two definitions here. A dominant pole is a pole which is nearer to the origin or which is having highest time constant. Insignificant pole is a pole which is away from the origin or which is having least time constant. So take down those two definitions also. Dominant pole. Definition: dominant pole is a pole dominant pole is a pole which is nearer. The dominant pole is a pole which is nearer to the origin. Dominant pole is a pole which is nearer to the origin or imaginary axis. Or you can say another definition, dominant pole is a pole which is nearer to the origin or imaginary axis, or is a pole which is having highest time constant. Dominant pole is a pole which is nearer to the origin or is a pole which is having highest time constant. Now in the same manner, then what is the insignificant pole? Now insignificant pole is a pole which is away from the origin, or is a pole which is having least time constant. Right? Now you see here, this is the dominant pole which is nearer and which is having highest time constant. This is insignificant pole which is away and which is lowest time constant. This is the dominant pole and insignificant pole definition. This is the dominant pole and this is the insignificant pole definition. These two are very important. See, in this question number 4 in our handbook, then see, around half an hour we are discuss the same question, because n number of concepts are there. What is the dominant pole? What is insignificant pole? What is the time constant? How to find the time constant if more number of poles are available? And what are the behavior of the system? The response depends upon which parameters, is only depends upon poles, depends upon zeros, or both. Now, how to find the system stability directly from the shortcut method? Then n number of points we can raise from this particular question. Therefore, all that particular points you just remember, and which is very easy and important for further discussion of our subject. Okay. Then in the next session we will solve a few questions related with the time constant, stability, and frequency of oscillation, such that and your time constant, your parameter calculations and everything will be very simple, and you have some familiarity of how to find the time constant, frequency of oscillation, order, and everything is also very easy for you. Okay. But if you understand this concept, then the remaining solvation of the questions are which is very simple once if you understand the concept. What is the concept? The total concept I am just giving in this particular single question, so such that it is very easy for you. That we will see in the next session. First you copy this definition and all these things.